In this video, I'm going to calculate the Fourier series for the function f of x as given here. The function is defined on the interval from 0 to 1, and it's minus 1 between 0 and 1 half, and it's 1 from 1 half until 1. And we're asked to find the Fourier series for the function f of x extended periodically. So what that means is we want to take this function f of x, and we'll take the part that we're given, which is where it's defined between 0 and 1, and we copy that over and place it periodically along the real line like this. So first thing to notice is that the period of this function is exactly 0 to 1 because we've taken the function on this interval and just copied it over. So that means for Fourier series we're going to have to set L equal to 1 half because L is always 1 half of the period. And that convention arises because of the way these Fourier series are used for solving PDEs. So L is equal to 1 half. And the Fourier series representation, I'll write it like this with an equal sign, and I'm just going to put an Fs underneath to make it clear that this is equals in the sense of Fourier series. It may differ at some points. And so I have an a0 over 2 plus the sum from n equal 1 to infinity of an cosine, and now it's n pi x divided by 1 half, and we'll put that in the numerator as a 2 in a moment, plus the sum from n equal 1 to infinity of bn sine of n pi x over 1 half. Now, if you look at this function, it's an odd function. It has the exact negative values if you go in opposite directions from the origin. Down here it's all -1, up here it's 1, and then it switches after a half and so on. So what that tells us is that when we calculate the Fourier coefficients of any even terms will be 0. So we don't really need to bother calculating the a0 term or any of the an terms because they should be 0 by the evenness of those functions. And so all we're left with calculating are the bn values. So let's do that. So the formula for bn is 1 over L integral from minus L to L of f of x multiplied by sine of, and now I'm going to take this half and put the 2 in the numerator. It's the same expression, just rearranging the fraction. So this is what we have to calculate the bn values. So let's fill in the pieces. L is a half, so 1 over a half is 2, and then this is the integral from minus a half to a half of f of x, and I'll just copy this over, sine of x dx. So now we use a shortcut trick, and this will often work, especially when you're dealing with an even or an odd function f of x. So you'll notice that if the function f of x is odd and the function sine of 2n pi x is also odd, their product will make an even function. And if you're evaluating an even function, the integral of an even function over a symmetric interval about the origin, then you can just calculate 1 half of that and multiply by 2. So I can take the 2 that's there already and multiply by another 2 and now just integrate from 0 to half, because the integral from minus a half to 0 would be the exact same value, so I just account for it with that 2. And this makes the calculation a little bit simpler. In particular, I don't even have to bother breaking up my integral into 2 different pieces because one of them is enough. It just goes from 0 to a half. So all I need is to put in minus 1 here times the sine of 2 pi n x dx. And that minus sign is convenient because the antiderivative of minus sine is cosine. So we get here 4 antiderivative of minus sine 2 pi nx is going to be 1 over 2 pi n multiplied by the cosine of 2 pi nx evaluated from 0 to 1/2. And so here I'm going to do a little bit of canceling. I get a 2 over pi n as the coefficient, and then cosine of 1/2 is going to be the cosine of pi n, and the half here and the 2 there, 2 there will cancel, so I have pi n left over. And then I subtract from that, and let me put a bracket in front. I subtract from that the cosine evaluated at 0, which is just 1. Now, cosine of n times pi, when n is equal to an even number, this will always be 1, and when it's an odd number, this will always be -1. And so we can replace that whole expression by 2 over pi times n minus 1 to the n minus 1. And these are the Fourier coefficients for the function that we've been given. Now let's try plotting this Fourier series in Desmos and see how well it approximates the function f of x that we were given. So y is equal to the sum from n equal 1 to, now I'm going to make it m, and then we'll make m large. I'll do that in a moment. And now here we need the coefficients. So those coefficients are 2 over n pi multiplied by minus 1 to the n minus 1, and all that gets multiplied by the sine of 2n pi x. And we need a slider for m, so we can choose a value, and m will be between 1 and, let's make it 30 in steps of 1. So that's the first approximation. As we improve on it, it starts to look more and more like our step function that we were given originally. You'll notice the approximation fails right at the jumps, so f of x is not exactly equal to the Fourier series right at a half, 1, 1.5, and so on. But everywhere else, for large enough sums, or if we go to infinity, they'll converge to the value of the function everywhere else.